Hello everybody, how's everybody doing? I hope you're doing fine, better than me. And it's quite a world out there today. Anyways, let me start again. My little sales pitch. I've uploaded a book, The Rope Hypothesis, and it brings you up to speed on what we talk about in this channel, which is the rope hypothesis. Proposing that all atoms in the universe are interconnected, okay? And if you have a second language, native language of some kind, we would appreciate if you contact us at tokakaka@hotmail.com and, propose that you can translate it to your own native language. And we'll send you a file that you can modify. Anyways, yeah, like I said, quite a surrealistic world out there. I'm here in Germany, in Frankfurt, and the province or the state here is called Hessen. The other day, about 4 or 5 days ago, economic minister of this state committed suicide. And the word around town is that he committed suicide because he couldn't stand his wife for 2 days. Okay. A lot of jokes that you hear out there today. We're full of jokes on this thing. So you don't know how to treat it. Yeah, it's quite surrealistic. Over here, if you want to take the only places that are open are really the supermarkets, right? And you go to a supermarket, you get your cart out. You used to put a coin in there to be able to pull that cart out and take it inside the store. Well, now all these, where you put the coin, it's all blocked with tape because they only allow like 20 people inside a store. Each store has a different number of people that they allow in there. And so once you get to 20 carts, the other guy has to wait in line for a cart. Otherwise, he doesn't get in. As soon as you go in, they spray your hands and the cart to make sure it's not contaminated. So I'm wondering, a lot of these things will continue probably after this whole thing blows over. How much of it will blow over, I don't know. A lot of people are staying at home and getting things through internet, like Amazon-like, and I don't know if that's going to change. I think a lot of people will switch over to that, and there's going to be less window shopping. Window shopping is going to be done online. And so I think there's going to be a lot of habits, a lot of behaviors that are going to change with this virus, not so much with the virus, but with what the politicians have implemented as a result of the virus, right? And so, yeah, keep that in mind. There's going to be some changes, and I don't know if we're going to go back to normal, okay? And about talking about going back to normal, that includes whether we're going back to the economic system we used to have. There's a lot of people that lost their jobs. I think there's like 3.2 or 3.3 million applications for unemployment in the U.S. alone, and other countries are in the same shape. So there's a lot of unemployment that's going to be out there, and I'm not sure you're going to recover that unemployment overnight. It's not like in 3 months, assuming this blows over in a month and a half, and then they pick up things, start picking up back again. I'm not sure we're going to go back to full employment overnight. It's going to take a while, and the question is whether they can. Remember, you're not creating manufacturing or agricultural jobs anymore. Now you're creating service jobs, nonsense jobs. It's unemployment jobs. And aside from that, there's this help from the government, giving money to people, giving money to companies so they don't go under, so they don't lay off people, that sort of thing. And what that does is create, a lot of money out there. And that's going to lower the wages, the salaries of people who, the proletarians, people who depend on their salaries. So yeah, it's going to be very interesting in the next few months what's going to happen. And well, a lot of you know my theory. I've been peddling it for 20 years. It's It's going to be economics that kills us. It's not going to be the climate change. That's nonsense. Not that it's nonsense whether the climate is changing. That's not the issue. The issue, it's got nothing to do with the extinction of man. It's not going to cause the extinction of man. Asteroids not going to cause the extinction of man. Disease itself, the virus, not going to cause the extinction of man. No. What's going to cause the extinction of man, according to my theory, is economics. Man's artificial economics, this economic system we created, this monster we created, this abstract monster we created called money. I think that's going to collapse. And I've written a couple papers, okay? And here you can see something about them. You can look them up there in the description. Okay, and you can find the link there. You can read them. Unsustainability, and we are the last generation of humans on Earth. Been peddling that theory now for 20 years. And, a lot of people don't like the theory. A lot of people don't believe it, especially anywhere from 20 to 40-year-olds. They don't like that theory. And it's not a nice theory to hear. It's like, the doctor telling you that you got 6 months to live. Who likes to hear that? So it's a very unpopular theory, and people always seek a second opinion. No, you got to think about it, in your mind. You got to crunch it in there for yourself and figure out whether it makes any sense to you. Now, a lot of people have criticized me and say, well, Bill, your predictions have not come true. And yeah, I'm a lousy astrologer. That doesn't make me a lousy scientist. Scientist deals with how, and astrologer deals with when. And, I have my own opinions, and again, I'm a lousy astrologer about when it's going to happen. And you should not throw the baby, with the bathwater simply because, the prediction didn't come true. I made a lot of predictions over the years regarding when it's going to happen. That was my personal opinion, but that's got nothing to do with the theory, which explains how, what the mechanism is. And that's what you're going to find in the descriptions. There's 2 papers there that I published, one in 2010, the other one in 2016. You're welcome to read them. They're for free, okay? Okay, what am I going to talk about today? I'm going to talk about a little bit about geometry. We were on this subject now for a couple of weeks. And I'm going to argue today that the Greeks set us off on the wrong foot. And not only have they set us off on the wrong foot, but we landed on the wrong foot. Today we don't have any valid rational notions of geometry. Okay, our foundations are rotten to the core. That's what I'm going to argue today, especially the issue of dimensions. Okay, so I'm going to get to that. And I'm going to pick on a little fellow who died a couple of years ago. His name was Stephen Hawking, and he was a relativist, and he made a lot of money selling his books and his theories regarding relativity, 4-dimensional space-time, 0-dimensional black holes. It was all dimensional, and a lot of that comes right back to geometry. Okay, so yeah, I'm going to look at geometry and then how it affects the theories that we have out there today. Okay, so where do we start? Well, here we have this fellow, and his name was Plato, and he had a sign on the door of his academy, and this is one version. I've seen several versions of this. It says, "Look, let no one destitute of geometry enter my doors." Okay, so Plato said, you got to know geometry if you want to be intelligent. Otherwise, you're a ignoramus. Okay, now the big problem I've got with geometry, okay, to begin with, okay, is that it's the first step in attempting to unite mathematics with physics. Okay, it's trying to apply mathematics to physical issues. Now, as long as you apply math to measurements and calculations, that sort of thing, well, yeah, that's fine. That stays within the realm of mathematics. Those are just descriptions. It's when the mathematicians take that extra step, and they say they now can interpret the universe, the workings of the universe, the invisible workings of the universe. You know, gravity, magnetism, light, electricity, those kinds of things. When they claim that they can interpret those thanks to their mathematics, now that's when we get into voodoo magic. And that's why we have only irrational theories today, especially out of quantum mechanics and general relativity. Okay, so that's the point I'm going to try to make today in general. Okay, so where do we start? Well, here we have Mr. Euclid. He was a guy who came 1 or 2 generations after Aristotle. No one knows exactly when he was born, when he died. All we have is his book, Elements of Geometry. And all we can do is, find out from his book what the notions that the Greeks had of geometry, which is the one that serves as a foundations for what we have today. Okay, and again, he came 1 or 2 generations after Aristotle. He very likely studied not only at the Lyceum that Aristotle had in Athens, but probably also at the Academy, which, Plato had died, but his students continued, and so this academy was still open. So he probably studied in both of those, more than likely. And then he wrote this book, Elements, which kind of synthesizes the notions that the Greeks had of geometry, about 200, 300 years before Christ. Okay, and so here it is. This is the first problem I find with Euclid, and that's his point. Okay. And again, I'm not going to beat up on Euclid alone because he got all this from his teachers, which means he just regurgitated what he learned in college. In those days, that was college, right? And he's got this no part point, meaning it's got no volume, no size, it's 0 dimensional, it's got no dimensions, and that's called a point. Big problem I've got with that, that's not a geometric figure. Okay, there's no such figure that is 0 dimensional. So we got a problem here because he starts out with this no part point, which no one can define to this day. Okay, and it turns out it's not a geometric figure because you cannot imagine something, a thing that is 0 dimensional, 0 volume, 0 size. Okay, there's no such notion. Okay, it contradicts the definition of what a figure is, what an object is, which is shape. Okay, so that's where the problem is. That's where it starts. So it's not a figure, and what they really use the point for, they don't claim it's a figure. At least that's not what it's used for. The word point is used to represent a location, and there you have a XY, 2 coordinates that give you a location, and that's what the point represents. So, these are pairs. They also have triplets and quadruplets and so on. Okay, and is that a couple numbers? Is that what a geometric figure is? Okay, so we got a problem with what geometry intends, which is a study of shapes, and to start out with this building block, which is called the point, which is 0 dimensional, no volume, no size, no dimensions. Right, nothing, and that's the building block. And they're going to use that also, remember, they're going to use that in quantum mechanics, and they're going to use that in general relativity. So don't dismiss the point as, well, very trivial. No, it's the building block of all of mathematical physics, that point. So that point is extremely important, and you can see it's misconceived from the start because it's not even a geometric figure. Okay, so where do we go from there? Well, we go to the line, okay, and here's the line. What's the problem with the line? The problem is, first, it's 1-dimensional. And again, there's no figure, no geometric figure that is 1-dimensional. Okay, that's the first problem. What you see there, the reason you can see it, it's 2-dimensional. That thing, that red thing that you see there has length, it has width and it has height. It has 2 dimensions at least. Otherwise, you wouldn't be able to see it. And yeah, there's no way you can represent a 1-dimensional anything unless you have at least 2 dimensions, scribbled with your pen or your chalk or your crayon. Okay, so that's the issue. So a line is not a figure, not if it's one dimensional, not if it's like Euclid said, breadthless length. If it's just length and it has no other dimensions, it doesn't have width or height, then all you're talking about is nothing. Okay, that's the problem. Okay, so we got a problem there, and that's the reason they can't define the word line today. They can't define the point. They can't define the line. Why? Because one of the issues is that an object is that which has shape, and you do not define objects. You point to them. Okay, that's what you do. You point. You point to a table and you say, "Look, table." Then you can describe it and say it's got 4 legs. A board over it, whatever. The point is that you point to things. You don't define them. So all the words in the dictionary that represent objects, you point to. Concepts, you define. And what they're trying to do is define objects. That's why they have problems also defining point, line, and plane, as we'll see. Okay. So the other problem with Euclid's line is that it extends incessantly, forever. And there's no object, no physical entity that extends across the universe and beyond. Even beyond God's heaven. No such monster, okay? All objects are finite. And if you have an infinite object, then you're not talking about an object because all objects are finite. An object is that which has shape. You should be able to visualize it. You should be able to draw it, whatever object is. Even if you're a poor artist, I'm a lousy artist, but I can draw a line. I cannot draw an infinite line. And the line that I drew is what they call a line segment, not a line, because the line is infinite. Okay, so we got a problem with that. There's no object called line that is infinite. Okay, that's the problem. And when we get to that next point, we see why. Because the line is not used as a geometric figure. A line is used to represent distance, displacement, time, and number. Okay, and when we talk about distance, it's not really distance. They're not talking about separation between two objects. What they're talking about is distance traveled, which is no different than displacement or motion or whatever. Okay, so that's what the line is used for. It's not used for geometry, which is first and foremost the study of shapes. Okay, and yeah, they're going to use that to make relations within objects and between objects. But that's different than saying that the line itself is a geometric figure. Okay, so we got a problem there with a point and with a line. Does it stop there? Well, no. Here we have it's an extension essentially, or a corollary of the line, which is the parallel lines. Okay, and Euclid attempted to define these. Again, it's the Greeks. He just kind of condensed all the information or all the knowledge that the Greeks had about these things, okay, their notions. And according to Euclid, lines should meet at infinity, okay? That should not meet at infinity. In other words, if they do meet at infinity, then they are not parallel lines. Well, the problem is, we must go to infinity to prove whether the lines are parallel or not. And that's not a definition. That's a proof disguised as a definition. Okay, they say, look, you got to run a test. Go and run to the end of infinity, if you can find infinity, or if it has an end, right? And find out if these two lines meet. And you go off and you never come back. So we don't know if the equal sign that we use in mathematics are parallel. Those two lines are parallel because those are line segments, and here they're talking about lines that extend forever. You got to find out if they meet at infinity. So again, that's a proof disguised as a definition. It's what they call an operational or functional definition. The true definition is equidistant lines, but what is an operational functional definition? Well, here it is. Let's put it over here. Okay, people think this is that operational and that these types of definition, operational and functional, are scientific. No, they're not. An operational definition, just a well-defined. These are from other people. I haven't. None of this is mine. I'm just giving you what I found on the internet. Okay, an operational definition is just a well-defined, repeatable, experimental procedure whose result defines a word or words. Well, that's not how we do it in science. We don't define words after running an experiment. We do it the other way around. We first run an experiment, and we first define and then run the experiment so we know what we're doing, okay? And then it says an operational definition requires an operation, a procedure, a way of measuring the variable of interest. And so what have they ended up with as far as operational definition? Well, here you have some examples. Weight is the numbers that appear when that object is placed on a weighing scale. Is that the definition of weight? No. Weight has certainly, you gotta know what weight is before you put anything on the scale. Operational definition of intelligence: I administer the Stanford blah 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 IQ test to a person and score the result. The person's intelligence is the score on the test. Great. So that's what it comes down to. That's what your intelligence shows up as, a number. We build operational definition for the words particles and waves. Now you know how they came up with particles and waves in quantum mechanics. They're operational definitions. They say, look, we didn't see something in there, but whatever it is, it has these two properties, and we're just going to define it on that basis. And then the last one, we explain what a carburetor is in terms of how it interacts with ignition chambers. No, you got to tell me what a carburetor is before you do anything with it. Okay? So yeah, all these definitions, operational and functional definitions, they're not scientific. Because in science we define first and then use the word later. You can't use the word throughout your dissertation and then say, oh, by the way, this is what I was talking about for the last 2 hours. This is an operational functional definition, okay? So what is a parallel line again? Well, that's what it is, okay? It's equidistant lines, okay? If they have the same distance separation, not distance traveled, but separation, we're done, and it's by definition. If they do have it, we're done. That's what we mean by parallel. So it's very straightforward in physics. You know what the word parallel means. Euclid's planes, well, here they are. His plane extended forever. It was made of lines, and lines extend forever, so do his planes. So what does an infinite triangle look like? Is it very different than an infinite square or a different circle? I mean, you know, when you say infinite, you lost everything. You have no shape, and therefore you don't even know if you have a figure. What is that thing that is so infinite, okay? And here you see breadth is a vector. And so I don't know if it was Euclid or the translator who used the word breadth, but breadth has nothing to do with dimensions. Okay, so if he was talking about dimensions, here you have a vector. Breadth is a vector. We'll see that in a second here. A plane is a type of figure that is expanding. Yeah, again, it expands forever. And again, like the line, it's infinite. And again, that's because of that, it's that a plane, the series of planes, if they're infinite and they extend forever, then they have nothing to do with geometry. They're talking about something else. They're talking about some concepts that have nothing to do with shape, which is the first and foremost requirement, prerequisite to belong to geometry. Okay, so what is a plane? Well, here I have it. Okay, I'll put it over here. And it's a category of rigid, continuous, smooth, ideal geometric figures that are two-dimensional. That's it. A particular face or cross-section of an ideal solid. If you have a cylinder, the end of it is a circle. If you have a cube, one end of it is a square, and so on down the line. That's what it is. It's the face of a solid in general, okay? Now, I'm not sure you can do that with every plane, but with at least the most important planes you can. Okay, that's what a plane is. Okay, and then it belongs to geometry. Okay, where does all this find a brick wall. Well, the notions that the Greeks and that they have today run against the brick wall. Well, here a good example is the circle. Okay, here's the definition of circle that all these people came up with. Euclid and Greeks came up and said a circle is a plane figure contained by one line, such that all the straight lines falling upon it form one point. From one point among those lying within the figure equal another one, equal one another. Okay, and you can see that on the lower left-hand corner. That's Euclid's circle, and the problem there is that all these lines they hit on a line that's going around, and the question is whether between any two lines there's another line, and if they are, they're all separate. Because, you know, a line is different than another line, a neighboring line. So there's got to be space between them. That means it's not a continuous figure, the circle, according to Euclid. Are we doing any better with the modern version? Well, they say a circle is the set of points in a plane that are equidistant from a given point. That's Wolfram who's got this in there. And the problem there is, again, the set of points. If each point is individual, each point is a separate, distinct entity from the one next to it, then it's not a continuous figure by definition. So we got a problem with these definitions because we're now talking about a continuous plane. We're talking about a segmented sort of figure, no matter how you look at it. To make matters worse, they say, look, and you can see that in the drawing next to Stephen Hawking there, they're going to rotate something around. Let's see what it is. And that's Wikipedia. It says, a circle is a shape consisting of all points in a plane that are a given distance from a given point. That's the same thing we had just now. But it says, equivalently, it is the curve traced out by a point that moves in a plane so that its distance from a given point is constant. Okay, so you got the relativistic circle there, the one that's used by mathematicians, which is just a bunch of dots, a bunch of points surrounding a center. Okay, there's nothing between the dots on the outside and the dot in the center. There's nothing there. In other words, what they're talking about is a ring in which none of the points are connected because all those are discrete points. So is this a geometric figure? Is this a plane? Are we talking about a ring made that are not even, where the dots are not even connected because there's always a dot between any two others? So we got a problem with those definitions because they're not talking about a geometric figure. And to make matters worse, the definition from Wikipedia shows us this. It says, look, if you twirl a point around, that's a circle. Well, is that a circle? Looks to me like an orbit, not a circle. I mean, you tell me. Okay, so what they do is they say, well, Bill, what you're talking about is not a circle. You're talking about a disk. Okay, you're talking about a figure that is continuous from edge to edge of that circumference that's surrounding it. So let's look at this. Let's look at these definitions that these people have. Okay. And here it is. Okay, it says the difference between disk and circle. Okay, look at this. Because I always thought the circle was a geometric figure. Now they're saying, no, that's the disk. The circle is something else. Okay, let's look at this. The disk is a thin, flat, circular plate or similar object with circle. While circle is geometry, absolutely not. A two-dimensional geometric figure. No, it's not. It's an itinerary. Or it's a series of dots which are not connected to each other. They just have the same distance from a center. Okay, that's not a geometric figure. That's a bunch of dots. That's all it is. Because there's nothing between the dot in the center and the dot on the edge. A two-dimensional geometric figure, absolutely not. A line consisting of the sets of all those points in a plane that are equally distant from another point. No, we don't even have a plane. Because if we have a plane, then you must cut it. Like if you're going to make a plane like for show and tell, okay, you can cut all around the paper and you can say, look, this is a circle. That's a plane, but or a representation of a plane. But I can't bring to the conference a bunch of points that are not even connected. I mean, I could bring, the best I can bring is a collar, you know, with all those pearls around it. But even those I have to connect with a little line so that people realize that it's all connected. So no, the circle of mathematics has nothing to do with geometry, okay? And shows the problem with their definition today. Now, whether they can use it in mathematics, irrelevant. You know, they can keep it there. I don't care. I just don't want them bringing that nonsense into physics. That's where the problem is. That's what I'm going to talk about today. Okay, disk, also disk, is the region in a plane bounded by a circle. Yeah, there's no region because there's no matter, there's no nothing between within the circumference, within one edge and the other edge of the circle. There's nothing there. All they have is a distance, they say, from the center point to the edge. That's all they have, a distance. There's nothing, there's no thing in there. Okay, that's what I want to make sure, okay, that you understand. A disk is said to be closed if it contains, okay, la la la. Circumference, what is a circumference? It looks like there is no difference between circumference and circle then, right? Well, they say circumference of a circle is the linear distance around it. So we got a problem here because they say the circle's all those dots around. That's so-called a geometric figure. But if you hop from point to point all around, okay, and you measure that distance, well, that's a circumference. So circumference has to do so-called with more with mathematics, like we need a number for circumference, and circle is the thing that surrounds the circle, the disk or whatever, right? So no, we got a problem with all these notions that mathematics has come up with, okay? And just to top it off, what they do a lot, which is totally illegal, okay, is this. They have the circle, the square, and the triangle, and they tilt them. They twirl them around. They say, oh, we still have a square. No, we don't, because all these things can only be seen head on. As soon as you move them in any way, they lose their shape. And in fact, if you put it straight, you know, like if you turn it 90 degrees completely so that the edge points at your eyes, it should disappear completely because a plane has no thickness. Okay, so we got a problem with all these people who start, you know, moving these planes around. You can't move a plane because a plane can only be seen straight on, you know, head on. Okay, so too many problems with what geometry has today. Foundations. I'm talking about the foundations. Okay, you say, well, so what's the problem with all this? So who cares? I mean, fine. Okay, so they screwed up with some of the basics. They don't have the definitions. They don't have a good idea of what these geometric figures are, but they use them and they can do a lot of stuff with it. Well, again, the big problem here is when they introduce all this stuff, this mathematical nonsense, when they bring it into physics and they say, oh, now I'm going to do physics with all this. See, geometry was the stepping stone into mathematical physics. And I argue here, and I will argue till my dying days, mathematics has nothing to do with physics, and physics has nothing to do with mathematics. Physics belongs to science. In physics, we must explain phenomena, especially invisible phenomena. We need to explain magnetism, gravity, that sort of thing. Mathematics can only describe. And the attempt to unite these two and create this religion called mathematical physics is what took us into nonsense such as black holes, space-time, Big Bang, traveling through time, and all this nonsense. And so it is important because this is the foundation, what you're seeing here. This is where it all started. It started with a point, with a line, with the Greeks. That's where it started. And that's how it developed over the last 2,000 plus years, okay? So here we have an example, and it's Mr. Stephen Hawking. Okay, and he died a couple of years ago. And you can see where some of the problems come in. Here you have unit of length called a light second. Light second. Is that a length? I thought length was, you know, the length of a table. You know, how long is a table? That's what length is. These people are talking about something else. They say, look, I'm going to time something with my clock. And I'm going to time how long it takes, or how much time it takes for a beam of light, for example, to go from here to there. So we're talking about two different things. That's not a length. That's, again, it shows how these people confuse length, which is like the length of a table, with measuring something with a clock, which is distance, not even distance, called distance traveled. Here I have a quick picture that shows length is what a box has. Okay, that's length. And distance is what's between two boxes. I synthesize distance is what lies between lengths. That's the correct way of understanding distance and length. What these people are talking about, they're talking about distance traveled. They always talked about measuring, unrolling the measuring tape. That's what both distance and length mean to a mathematician. And therefore, they've always introduced this distance traveled as distance or as length. And in fact, if you look up the words distance and length, you'll find that they're synonyms, perfect synonyms in mathematical physics. Not so in physics. And in his book, A Brief History of Time, Hawking defines this in his glossary. He says, a point in space-time. So now that's what an event is. Here you have an event which is something that happened, and he's going to use a point to represent it. A point is a static object. I mean, assuming it had shape, and it turns out it doesn't even have shape, but let's assume it has shape. It's a dot, right? Are you going to represent something that happened, a movie, with a photograph? Are you going to represent an event with a dot? Makes no sense. These people are saying that an event is just a point. And they're going to build space-time with all these points, all these happenings that happen supposedly in zero time, because that's what a point is. Point has nothing to do with time, whereas event does. And you can see also that they've got a little bit of a contradiction there between field and elementary particle. A particle supposedly is a field, a vibrating field. What is it that is vibrating? Well, it's a field that's vibrating locally, okay? But when you go to field, it says something. Again, they never define something that exists. They never define exists, even though they use these words every 2 seconds, right? Something that exists throughout space and time. In other words, a field covers all of space-time. We're done. We don't have to identify it. We don't have to know what it is. We just say it covers all of space-time. So what is an elementary particle? Well, it's one that cannot be subdivided. And and what is a particle? A particle is just a vibration of the field locally. And what does that mean as far as size and so on? Well, it's got no size. It's just an infinitesimal part of a field. So you can see how they get away with all this stuff, because they are manipulating the language here. It has nothing to do with reality. It just has to do with language, with semantics. That's what they're doing. Okay, so here's good old Stephen Hawking, and he continues in his book. He says, one could specify that a point was at a certain latitude and longitude and a certain height above sea level. One is free to use any three suitable coordinates. Height is a coordinate? I thought height was a dimension. I thought we had length, width, and height were dimensions. If I got it right, I don't know. Maybe I got it wrong. You correct me, right? And we had latitude, longitude, and altitude, and those were coordinates. And these people mix coordinates, dimensions. They don't care. They mix them all together. You saw the word breadth, which is a vector. They bring that in there. Depth, breadth, and elevation. They bring that all the same to them. And it's all the same because they're not talking about dimensions, coordinates, or vectors. They're talking about number lines. That's the issue. The issue is number lines, okay? And so we have to educate them a little bit. Here's a good chart that puts it in the right perspective. Dimensions, they have to do with orientation and tilt, that sort of thing. You have length, width, and height. Straightforward. Babies can understand this, except mathematicians. Coordinates, they have to do with location, and they point inwards towards the object. Okay, longitude, altitude, and latitude, they come towards the object. And vectors have to do with motion. They have nothing to do with orientation, location, dimensions, or coordinates. They have to do with the motion of an object in three mutually perpendicular directions: depth, breadth, and elevation. What are the mathematicians talking about? They're talking about quantitative stuff. They're talking about number lines. And number lines have what dimensions, coordinates, and vectors don't have, and vice versa. These have properties or attributes which number lines don't have. A dimension, coordinate or vector, has two properties. It's mutually perpendicular to the other two, and it's got direction. And number lines have neither one of those two. Number lines have magnitude and do not have direction or perpendicularity to anything. And so we got a problem because these people are using the words of physics, for example, length, width, and height, to talk about number lines when the physical notion of length, width, and height has nothing to do with numbers, and numbers have nothing to do with dimensions. And that's how we get to four-dimensional space-time. So keep that in mind. That's how they came up with 4D space-time. No, it's four-number-lined space-time. They're not talking about dimensions, vectors, or coordinates. They're talking about numbers, okay, which has nothing to do with physics or with dimensions, coordinates, vectors. Okay, here's another thing that you get out of Stephen Hawking's book, which is relevant to dimensions. It's easy to draw diagrams of two-dimensional spaces, whatever that is, okay, such as the surface of the Earth. The surface of the Earth is two-dimensional because the position of a point can be specified by two coordinates, latitude and longitude. Well, I'm sorry to tell Mr. Hawking, but it looks like he's a flat earther. He's talking about this, I guess. You know, he's saying in two dimensions, he's gonna or two coordinates, latitude and longitude. He's talking about this. He's saying, look, you got the map there, right? And you can locate any point with latitude and longitude. You only need these two coordinates. Well, yeah, that's if you have a Mercator map. You know, I guess he's talking about the flat universe, flat Earth that he probably believed in or confused it with. I don't know. The Earth has, for his information, has a little more than two coordinates. It's got a third one. Okay. Did he forget about radius, the center of the Earth to that point there that he needs on the surface of the Earth? Yeah, you need three, or he's taking it for granted. He's saying, look, we can go move around the Earth. No, if you move around, then you're cheating, because you're treating the Earth as a flat surface. You can't do that. Either the Earth is round or it's flat. You know, we can't have it both ways. So if you only need two coordinates to locate a point on the surface of the Earth, you're a flat earther. We're done. Okay, that's how simple it is. So no, you need three. But he takes the third one for granted, which is actually the altitude. Okay. Okay. What else does Mr. Hawking say that kind of, you know, is counterintuitive? Okay, and he says the following. This is all in his book, by the way, 1988. Okay, famous book that he made a lot of money with. One can use a different set of three coordinates, okay, to specify the position of a point, okay? An event is something that happens at a particular point in space in a particular time. So one can specify it with four numbers or coordinates. We need four numbers or coordinates to specify an event. I thought he said he just needed two coordinates to locate a point on the surface of the Earth. Now he's got two more. Now he needs four. Okay. Again, the choice of coordinates is arbitrary. One can use any three well-defined spatial coordinates and any measure of time. In relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any two space coordinates. So he's saying time is no different than space as far as these little engine arrows that he draws. They're all the same to him. Why? Because they're all number lines. That's why. I mean, qualitatively, you know, hopefully height and width and length are a little qualitatively different than time. The others are, you know, static. They don't move. You just point, say length, width, height. We're done. And time is something that rolls along to infinity, probably. Who knows? I mean, as long as we live forever, you know, you're going to have comparisons of two motions, which is the definition of time. And so time runs runs, period. We don't have to say forever or anything like that. We just have to say time runs. Whereas length, width, and height, they don't run. They don't move at all. They're static concepts. So to say that there's no difference, it means you're talking about math, not physics. Okay? Again, it's the attempt to introduce these notions into physics that is offensive. Okay? And he illustrates this time dimension that he talks about, and here it is. Okay? He says, I shall generally use diagrams in which time increases upward and one of the spatial dimensions is shown horizontally. Okay, he's got two dimensions there horizontally. He calls them space. I don't know of any dimension called space. I know of one called width, the other one called length, another one called height, and he replaced the height one with time. The other two spatial dimensions are ignored. Oh, okay, yeah, he couldn't fit them in there, so he ignores them. He says, oh, let's get rid of them. We don't need them. And these are called space-time diagrams. Well, yeah, I guess, if he says so. Again, what does this have to do with physics? This might be useful in mathematics. I don't know. Maybe it's good for them. But it's got nothing to do with physics. Okay. And here you can see a little bit of why. Here's the coordinate system is, what a coordinate system is, especially the famous Cartesian, Descartes, Cartesian coordinate system. A coordinate system is a system that uses one or more numbers. What is a coordinate? It's a number. Does that have anything to do with physics? Absolutely not. Okay, so we got a problem because these people are saying that a coordinate is just a number, and that's not what a coordinate is for the purposes of physics. Physics, it has to do with locating an object. So that's why you have latitude, altitude, and longitude, okay? Because they locate an object. All we want is qualitative location. That's all we're interested in. But here these people are using numbers. They say they're going to measure something, I guess. Or coordinates to uniquely determine the position of the points or other geometric elements on a manifold such as Euclidean space. In other words, what they're doing is they're taking measurements and they're calling these measurements number lines. They're calling them dimensions, or they're calling them coordinates, or they're calling them vectors. That's the problem. And there you see Wolfram, a set of variables, also for the word coordinate, right? A set of variables which fix a geometric object. In other words, fix the location. I guess that's what they're trying to say there. If the coordinates are distances measured along perpendicular axes, they are known as Cartesian coordinates. Again, what are we talking about? Well, we're talking about, again, measuring, and we're talking about numbers. We're not talking about physics, okay? But this is what they're going to use. And remember, they're going to use this for determining space-time, black holes, all that stuff. That's based on all this nonsense, on these notions. Okay, so yeah, they have all these weird notions that they created in math. They simply extrapolated them into physics, saying, "Oh, we're mathematical physicists. We're not just geometers or mathematicians. We have something to do with physics. We're going to interpret the world for you." Okay. Okay, here's another notion that Hawking has. It is often helpful to think of the four coordinates of an event as specifying its position in a four-dimensional space called space-time. It is impossible to imagine a four-dimensional space. No kidding. I wonder why. Why is it impossible to imagine? I mean, Jesus. I mean, if you can do it with math, and math represents the physical, real world out there, oh, I don't see what the problem is. We should be able to take all these numbers, because that's what a coordinate is, right? And that's what a dimension is. It's just a bunch of numbers, right? You should be able to take these numbers and visualize the real world, because they say these numbers represent the real world. And they can put a bunch of numbers. They can put 5 numbers, say it's 5-dimensional, and you go out there, you don't see these numbers. All you see is length, width, and height, which is 3 perpendicular directions. Now, if you can think of a 4th or a 5th perpendicular direction, it's because you had too much beer to drink, okay, or you were hit by the virus or something, Yeah, we got a problem with all these notions, okay? They have nothing to do with science or with physics, okay? Here's what he's referring to when he's talking about four-dimensional space-time, okay? When you look it up, you know, what is this space-time thingy that they're talking about? Well, here you see it, okay? This is what you get when you look up the words space-time. You get all these fish nets and spider webs. What are those? Especially, what's the background what serves as background to the fish net? Because if the fish net is space-time, what is the black stuff that serves as, or the white stuff in the case of the one on the lower left? What is the background? That's what we need to identify. I mean, we have space-time, and what is the other one? Love? Is that what it is? Okay, so we got a problem with their conceptualization. They should be able to conceptualize it on the board before they can make claims of this nature. Okay, here's one famous four-dimensional object which they use constantly to simulate space-time, or to show you that it is possible to imagine or to conceptualize, visualize, you know, space-time, because you start with the hypercube. Okay, here it is. Is that what space-time is? Okay, well, what are we staring at? What is this nonsense? All I see is a three-dimensional whatchamacallit that is superimposed or projected onto a two-dimensional platform or background. I don't see anything four-dimensional in that whole picture. Okay, and so let's find out what this space-time or tesseract or hypercube or hypersphere, for that matter, what are these things? Let's find out. Okay, and here it is. Okay, here you can see what they really mean by this. They construct their figures, and what it is a cube that is expanding through time. Okay, so we're talking about a cube expanding, and what they do, they take a photo of this movie called an expanding cube, and so they have, what they ended up with is with nested cubes, one cube inside another. That's what it is. And the only question you should ask yourself is, what are those lines that connect the vertices? In other words, what are those slanted lines that go from one corner of one cube to the corner of another cube? That's what we want to know. And what that is time. Okay, what you have is a cube that's expanding, and that those 45-degree lines, those are that's time. Okay. So it doesn't stop there. Then they go through the other step when they start. If you look at the next graph on the bottom on the right, that chart, you see that the cube expands horizontally, but then they take all these pictures of movies and they make another movie out of those movies. We have a movie of movies because they start moving the tesseract around as if they're moving an object, when what they're really doing is moving time itself. And here you have a little picture of that, okay? Okay, here it is. See, what you're staring at is two nested cubes, one smaller inside another one. The slanted lines that connect the vertices, those are, that's time, because the little cube is actually expanding, forming the big cube, and when that finishes, only can you move the cube to the next position or location. And so what you have is a movie of movies. That's what a tesseract in a rotating tesseract is, or hypercube. Okay, so this is what they've come up with all their dimensional analysis on this poppycock that mathematical physics has invented. It's not, you can't even conceptualize or visualize, because once you understand what they're putting in front of you, then you know it's bunk. It's all nonsense. It's poppycock. And they say, well, you got to take a course at university to understand it. Yeah, I guess you do. You need that brainwashing, you know, to really understand it, right? Okay, so what are the main points today? Let me just summarize here. Okay, let's see if we can run through them so you take something home with you. The Greeks set geometry on the wrong path, on the wrong foot, okay? And we ended up on the wrong path because we haven't made any progress since the Greeks. All we did is twiddle around a little bit with the definitions. What these people never figured out is you cannot define geometric figures. You point to them, okay? You have to point to a geometric figure. Circle, circle. Cube, cube. Point, if it's a dot, yeah, I can point to a dot. I can't point to zero-dimensional, no part point, okay? Zero-D point is not a figure. 1D line is not a figure either. It represents motion. The other one, the point represents location. Location is not a geometric figure. Motion is not a geometric figure. So to say that you're going to use the line to represent motion, displacement, distance, whatever you want to call it, whatever, or time, you're not representing a physical object. You're not representing a geometric figure. You're using a geometric figure, which is not 1D, it's 2D, because that's what you're going to put in there. You got to see it. It's got to be at least 2D. What are you using it for? You're using it to represent pictorially a concept. It's like using the heart to represent love. Say, here's love. No, that's a heart. That's not love. And that's what they're doing. They're saying, here's time. No, that's not time. That's a line. And that line is two-dimensional. It's a plane. It's not a one-dimensional anything. That's the problem. So we got a lot of contradictions, got a lot to do with language and failure to define. So if you wonder why point, line, and plane have not been defined to this day, now you know why. Because you don't define a triangle. You point to it. Okay? You can define the word plane, as a category of figures. That's okay. Same with line, same with dot, with the point, if you can define it as a category. But that's not what they're doing. They're saying, look, a point is that dot that I put on the board. Well, that's two-dimensional. Well, no, it's a pictorial representation of a point. Oh, what's the point? That's a location. That's the problem. It's a circular argument, okay? Okay, no object is 0D or 1D. Okay, parallel lines are equidistant. Okay, that's what it is. You don't prove that two lines are parallel by going to infinity, because you'll never come back. You'll never prove it. Okay, so this is nonsense. No, it's equidistant lines. They have the same distance, and by distance I don't mean distance traveled. There's no measurement involved. All you say is they have the same separation by definition. Okay. And no such thing as an infinite plane, which is made of infinite lines, or lines that extend infinitely, right? Location position is not a set of numbers. Okay, you don't say that the location of something is a number or two numbers or an ordered pair or a triplet or whatever. No, that's not a location. Location is a qualitative concept, okay? And you just have to have separation, okay, from something. Then you have location with respect to a house, a tree, a rock, whatever. Okay, okay, no object is 4D because it's unimaginable. And that's why, this nonsense about extra dimensions beyond the three that we, our experience tells us, they're selling you, snake oil. You drink a lot of Kool-Aid there, right? Time is not a dimension, it's a number line, okay? Math has no use for dimensions, coordinates, or vectors, the qualitative notions we have in physics. That's why they dismiss that as, well, that's baby stuff. Yeah, that's what we use in physics, the baby stuff. What do they say? What do they use? They use number lines, which they call dimensions, coordinates, and vectors. But ask them to label and tell you what is the name of each one of their 4, 5, 6, 26 dimensions. What is the name of them? And what are they going to do? Length, width, and height. And what are we going to say next for dimension, for example? They don't have a name for it because, I guess they ran out of names. There's no such monster. Okay, these people are talking about stuff they have in their head, not something that's out there in reality. Keep that in mind, okay? Okay, math only has use for number lines. No such thing as a 4D space-time, okay? Space-time is a concept, so you can't say that you live within a concept called space-time. No, all we have is atoms in the universe which have distance and location separation and location with respect to each other. That's all we have. That's what is out there. That's reality. Anything beyond that means you've been brainwashed. You need to see a psychiatrist, okay? 4D space-time is a 3D object in motion. That's what they're talking about, as you saw with the Tesseract, okay? Hypercube is a movie of time in motion. They don't even realize this, that one of the legs of the hypercube is time. And they have time, why? Because this cube is growing. When they turn that around, they're moving time around. That's what they're doing. You might say, Bill, you're crazy. No, that's what they're doing. Believe me. Look it up. Find out what those lines are. They're time. That cube is expanding. The fourth dimension is time. Okay, so you have length, width, and height. That's the cube. Where does time come in? Well, that's in the growing. Okay, so they have this cube that's growing, and that's time, and now they twirl that around. They've got a movie of this thing going up. Once it finishes growing up, not while it's growing, but once it finishes, you got your first cube. That's your first frame of your next film, which is made out of all these nested cubes. That's what you're staring at when you're seeing the tesseract or hypercube rolling. So it's all nonsense. Anyways, I'm going to continue along this line on what's next? Sunday? We'll see you on Sunday. And I hope you have some food for thought. Bye-bye.